Okay, do you guys have any questions first before I go on to 5.2? Okay. So 5.2 is about the summation notation stuff again. So let's just recall what that is. I've got a sum, and there's an index set, usually the integers, and so the index value starts somewhere and ends somewhere. This is the index variable. This is the starting index value. And this is the ending index value. Let's try that again. And in here is some function of the index value, right? And this just means we're going to take f of a plus f of b, plus a plus 1 plus f of a plus 2 plus ... plus f of b minus 1 plus f of b. So I'm going to add up for each index value between a and b inclusive. I'm going to put that index value into the function, and then I'm going to add up all of those different values that I get out. Make sense? So let's do some examples. Sum from I equals 5 to 8. Let's go 1 over I plus 1. So I put 5 in, I get 1 over 5 times 6, plus I put 6 in, I get 1 over 6 times 7, plus I put 7 in, and then I put 8 in. And I add those things up, and that's what I get for this summation notation. Sometimes the index variable isn't I. I just makes a good index variable because I is the first letter of index, but sometimes it's n. So n equals 2 to 8. Again, let's go n squared. So that's 4 plus 9 plus 16 plus 25 plus 36 plus 49 plus 64. Just any questions on the notation stuff? I can have an infinite top bound. Let's go 1 over n squared. This is one, sorry, I better start at 1 if I'm going to go from n squared. So I can go 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus, and this just keeps going forever. I keep adding smaller and smaller things. This is actually pi squared over 6, I think. I'd have to look that up, but I think it's pi squared over 6. If you add up the reciprocals of the squares, you get a nice number like that. And so you can have infinite sums where the sum just doesn't have a terminating index value. You can do things like this, where then this is add up f of I for every I in the set I. So I could do the sum of P prime 1 over P squared. So this would look like 1 over 2 squared plus 1 over 3 squared plus 1 over 5 squared plus 1 over 7 squared plus 1 over 11 squared plus 1 over 13 squared plus dot, 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 forever. Okay. So it doesn't just have to start at a certain number and end at a certain number. You can put a set of things that you're going to add up down there. You kind of indicate it by either an index set where the index value is contained in that set, or you just describe what the index set is down there. Okay. In this class, you probably won't see things like that, but they are useful in other places, and it just makes this summation notation even more useful than from certain values to certain values. Okay. There's a few algebraic things that you can do with these summations. So some summation rules. Okay. If I have the sum of AI plus BI, where the function now is indicated by a subscript because I think of these as sequences instead of just actually A of I and B of I. I equals, let's go S to T. Well, that's the sum from I equals S to T of the AIs. Do those first and then add them to the sum of the I from S to T of the BIs. So if I want to split up a summation, I can do it by splitting it into two summations. Kind of makes sense, right? Like if you're adding up a bunch of things, well, this is A1 plus B1 plus A2 plus B2 plus A3 plus B3 and so on. Well, just put all the A's on the left-hand side, all the B's on the right-hand side, and add parentheses. That's all this is. This does not always work when T is infinity, right? Not always does this work with T infinity, but for finite sums, this always works. And by finite, I just mean I'm adding up a finite number of things, not that the things that I'm adding up are finite. All the ways, whatever it is, you're adding up finite values, but you're not adding up necessarily a finite number of values. If there's an infinite number of primes, that's an infinite sum instead of a finite sum. Okay. The difference works too, so I could put a subtraction on here instead. Sort all the minuses to the right-hand side, all the pluses to the left-hand side, or basically you're factoring out a -1 from all the BIs and you're just using the plus, basically. If you have a constant and you're multiplying that constant times each of the index values, you can take that constant times the sum. Sorry, indexed values, not index values. So you can factor out the C from the summation. That's just the distributive property. This is commutativity and associativity. And the last one, if I'm just adding up a finite number which doesn't change at all, right? The index variable is I just add up C a whole bunch of times. So this is C plus C plus C plus C, 1C for every number between S and T inclusive. This is going to be C times the number of things that I have there. How many values are there between S and T inclusive if they're integers? How many integers are there? It's a harder question than you might think. It's a harder question than you might think. But how many numbers, how many integers are there between S and T, including the two endpoints? T minus S plus 1. Why do I have to add the 1? Yeah, T says start with T things. S says take away the first S of them. But I want to include S, so I have to add the S value back in. That's what that is. Okay. This is a fence post problem, basically. Okay. And so the special case of this is I equals 1 to n of C equals n times C. If you start at 1 and end at n, you take n minus 1, but you add the 1 back in after you subtract it off. So you've got n values there that you multiply by C. Okay, this is a special case. Okay. There's a couple more sort of finite sums that are nice to know. And we're not going to prove them in this class, but they are easily provable. And that's like the sum n equals 1. Let's go k. We'll use k as our index variable here. K equals 1 to n of k. So I take 1 plus 2 plus 3 plus 4 plus 5 all the way up to plus n. Well, that's going to be n times n plus 1 over 2. Has anybody seen that proved before? Well, you just rewrite it the other way. This is also equal to n plus n minus 1 plus ... plus 2 plus 1. And you add those up, you get n plus 1, n plus 1, ... n plus 1, n plus 1. So you get that 2 times this sum is equal to, well, there's n terms there, n times n plus 1. Each of them is an n plus 1. So you just divide the 2 over and you get your sum. Okay. Okay. K equals 1 to n of k squared. That one's a little harder. Does anybody know what that one is? So it's n plus 1, 2n plus 1 over 6, which is a little strange. but it works out that that's how that works. And you can do some geometry, some pictures about like why that would work, but I don't really want to spend some time proving that. K equals 1 to n, k cubed. That's n plus 1 over 2 squared. And there are some reasons why this guy is the square of this guy, but they're a little subtle. But those are three summations that are going to be kind of nice for us to know when we're doing this integration stuff here. Okay. Maybe we should see some examples. What's the sum from I equals 10 to 20 of I? Well, I'm going to rewrite this. This is the sum from I equals 1 to 20 of I minus the sum I equals 1 to 9 of I. And that's going to be 20 times 21 over 2 minus 9 times 10 over 2. So that's going to be 420 over 2 minus 90 over 2, which is 210 minus 45 is 165. Yeah. So if I add up the numbers from 10 to 20, I get 165. Questions on that one? So this says start at 1 and go to 20 and add them all up, right? I only want to start at 10 and go to 20. So the ones that I don't want to add up are 1 through 9. So I have to take away the ones that are 1 through 9. Does that make sense? Okay. How about I equals 1 to 100 I squared. So that's 1 plus 4 plus 9 plus ... plus 10,000, right? Will be pretty big. Well, the I squared summation is n plus 1 and 2n plus 1 over 6. And that's a big number that I don't know how to multiply in my head very easily. So we're going to leave it at that. I equals 1 to 5 of I cubed. 1 plus 8 plus 27 plus 64 plus 125. Well, I could do just that addition, but I could do it as 5 times 6 over 2 squared, which is 15 squared is 225. So I could figure that out, that it's 225 just as easily. And so this adds up to be 100 and then 225. 9 and 27 is 36, 36 and 64 is 100 and a 125. Okay, so that's our sort of basic summation stuff. Let's do some Riemann sums with limits now. So let's say I want to find the area under f of x equals x squared from, say, x equals 0 to x equals 1. So I draw a picture. Here's 1. Here's my parabola, ends at 1, 1. And I want to find that area. Make sense as a question? Okay, we've gotten how to approximate the area with rectangles, right? And we can use left-hand rule, right-hand rule, midpoints, maximum sum, minimum sum, lower sum, upper sum. Okay, because all of the functions that we're dealing with are smooth and continuous, no matter which type of sum I use, if I take it to the limit and I throw in as many rectangles as possible of equal width, it's going to come out to be the exact area that I have. But that only happens with nice functions, and nice in our case is continuous. Okay. So let's see if we can come up with some rectangles here and write down a sum that depends on how many rectangles I take, add them all up, and then whatever value I get, I can take a limit as that end value, the number of rectangles goes to infinity, and that'll tell me the exact sum that I have. Sounds a little complicated, but we'll get through it. Okay, so the first thing we have to do is we have to decide, we're going to write down, break it into n equal width rectangles. Okay, so I want n rectangles and they're starting at 0 and they're ending at 1. So how wide should each of the rectangles be? One over n wide. The width of the rectangles, that delta x, is 1 minus 0. It's the starting value minus the ending value, or sorry, the ending value minus the starting value divided by the number of rectangles. Okay? If I have n rectangles, each 1 over n wide, together they are 1 wide. Okay. So I'm going to draw an arbitrary rectangle in here. I don't know where it is, but I know that if this is the kth rectangle, it starts at k over n and ends at k plus 1 over n. Are we good with that? The kth rectangle, there are 1 over k, 1 over n's in front of it. So at this point, I will be at k over n, and then the next one will be 1 over n further along, which is k plus 1 over n. Kind of good with that? Okay, so the area of the kth rectangle is, and we're just going to use the left-hand endpoint because that makes everything a little bit easier. It's going to be 1 over n wide times k over n squared tall, because this point here, this is at k over n, comma k over n squared, because my function is the squaring function. Does that make sense? If I'm using the left-hand endpoint of this rectangle to figure out how tall it is. Okay, this is true of any of the rectangles, right? If my k over n was over here, this is k plus 1 over n. This is still the point k over n squared. So that rectangle is still k over n squared tall and 1 over n wide. So this makes k a very nice index variable to add up all these rectangles. So the area of all n rectangles, that's going to be the sum from k equals 1, the first rectangle, to the nth rectangle. Sorry, I want to start at k equals 0 and go to the n minus first rectangle. Why do I want to start at 0? Yeah, I'm using the left endpoints. So the first rectangle is the one that has the 0 as its height. The next one is 1 over n as its height, and so on. If I was using the right endpoints, I'd start at 1 and end at n. But then I'd have the height would be k plus 1 over n squared. Okay. So then I multiply by 1 over n, and then I multiply by k over n squared. All good so far? We can do some algebra now. N, k. Some of these things are fixed in this problem right now, at least for now, right? K is my index variable. K is the thing that's changing from 0 to n. The n in this situation, for every term in here, is the same n. We're good with that? So I can factor out this n and these two n's outside. So that's 1 over n cubed on the outside. And then I've got the sum from k equals 0 to n minus 1 of k squared. Good with that? Just a little algebra there. Okay. And this is a k squared summation, which I told you how to add that up before, right? The k equals 0 term is 0, so that doesn't really affect anything. And the sum from k equals 1 to n minus 1, that's n cubed times n minus 1, n minus 1 plus 1, 2n minus 1 plus 1 over 6. Yep. I will in a second. I just wanted to make sure that we were using this formula up here, right? We're using this formula with n replaced with n minus 1. Right? Okay. Okay, so now I can simplify that a little bit. I get 1 over n cubed. I have n minus 1, n, and that's going to be 2n minus 1. And that's going to be over 6. We want to know the area under the curve. So we're going to take n as n goes to infinity and find a limit of these approximations. This is an approximation using n rectangles of the area under the curve. As I use more and more rectangles, my approximation should be getting better and better. If it comes to a limit, we'll say that that limit is the actual area. Okay. So we get better approximations as n goes to infinity. We'll take a limit to get the actual area. Okay, so we're going to take the limit as n goes to infinity of, what do I have here? I've got n minus 1, n, 2n minus 1 over 6n cubed. We could use L'Hopital's rule, or we can multiply this out, but we know from algebra, the easy way to do this is take the leading term divided by the leading term. Take leading term divided by leading term. And that's going to be, the leading term up here is going to be 2n cubed, because I take the leading term of each of these factors and multiply them together to get the leading term of the entire thing. And the denominator only has one term, so that's n cubed. So this is 1/3. And the area under that curve from 0 to 1 is 1/3. Okay. Questions on that process? Yeah. How do I know that I can pull this out? Okay. So in my problem, we decided at the very beginning, n was the number of rectangles we were going to use, right? And that number stayed fixed until I decided to take a limit down here. So at this point, n is just a constant value. Does that make sense? And so it does not depend on k at all. K is the only thing that changes in this summation, right? The thing that changes is this bit right here every time that the index changes. Okay. Everything else in here we can think of as a constant because it doesn't depend on the index variable. Okay. Other questions? Okay. Let's try a bit more abstract, not much, but a bit. So here's f of x equals x. And if I tell you to go from 0 to a, you're going to tell me, well, it's just a triangle, so I'm going to take 1/2 the base times the height, right? But let's not do it that way. Let's do it this way. So we already know by geometry that if this is a and a, this is going to be a squared over 2 equals the area. Well, this is under the curve from 0 to a, if f of x is okay. So let's make sure that our geometry formula and calculus jive, right? They're like telling us the same thing if we do the calculus and our original geometry. It'd be really bad if calculus was not telling us what geometry has already told us. So let's make sure that that's the case. Okay, so we need n rectangles. N rectangles. Each width is, what is the width between these two what is the width of any one of these rectangles if I break up the area from 0 to a into n rectangles? A over n, right? The total width is a, so if I want to break it up into n pieces, I'm just going to divide it by n, and each piece is going to be a over n wide. I'm going to make that a little bit bigger. Maybe that one. Okay, so in here somewhere is a over n times k. That'll be the kth one that I start with. And this side will be k plus 1 times a over n. Each of them is a over n wide. So to get to the kth one, I will have had to use a over n k times, and then the next one I will use it k plus 1 times. Does that make sense? Okay. We'll do the right-hand endpoint this time. So this time we'll use an overestimate. It doesn't matter, but we'll use an overestimate. So I'm going to go at k plus 1, a over n is how tall this thing is from the right-hand endpoint, because this is my point. My point is k plus 1, a over n. comma k plus 1a over n, because my function is just output equals input. Okay. So that's the area of one rectangle, of the kth rectangle. A over n wide, k plus 1, a over n tall. Right? So if I want to add up all of these, I'm going to start at k equals, well, I have to start at k equals 0 still, because my first rectangle is when k equals 0. I'm going to go up to, what am I going to go up to? I'm going to go up to n minus 1, because there are n rectangles. K equals 0 is the first one, n minus 1 to n is the last one. I have a width of a over n. I have a height of k plus 1 times a over n. And we get this summation. What stuff is constant in here? What stuff can I factor out? What's my index variable? My index variable is k. Does a depend on k? No. Does n depend on k? No. K depends on k, so this doesn't get factored out, but the a over n bits, they get to be factored out. Okay. So I get a over n squared on the outside, and then I get on the inside the sum from k equals 0 to n minus 1 of k plus 1. Okay. All right, let me think about this summation a little bit and change my indexes. This sum, when I put k equals 0 in, I get 1 out. When I put k equals 1 in, I get 2 out. So this goes from 1 to 2 to 3 to 4 and so on. We're good with that bit. And then it's going to stop. When I put n minus 1 in, I will get n out. Okay, so I could re-index this as the sum of a to n squared times the sum of, let's index it with a j instead, but j is going to start at 1, end at n, and I'm just going to add up j itself. Okay, this is a change of variable substitution. This substitution and that substitution to change the index is that j is equal to k plus 1. If j equals k plus 1, j minus 1 equals k. And so if I put, let's do all of the little bits here. Move some stuff over this way. This substitution just comes straight down as a j. We're good with that part. Okay. Let's go purple, because this substitution, I'm going to use this. I'm going to get j minus 1 equals 0, which tells me j equals 1. And that's going to go down there. Up here, what this says is I want to stop when k is equal to n minus 1, right? So this is telling me I go from k equals 0 all the way up to k equals n minus 1. So I've got this expression up here with k equals n minus 1, which tells me that j minus 1 equals n minus 1, which tells me that j equals n, and that's going to be where I stop here. Okay. So you can do a substitution to change your index. Really, it's just shifting everything one way or the other by a fixed number of counting spots. This was kind of a simple case, so you could probably see it without actually doing that algebraic summation, but sometimes the harder cases You have to do that substitution to get through it. Okay. That was maybe too much detail, so we're back to this point here. And we've got the sum of these rectangles' areas is a squared over n squared times the sum from j equals 1 to n of j, which we know that summation is n plus 1 over 2, right? So I can cancel out one of the n's. I will get a squared over n times n plus 1 over 2 as the area under the curve if I'm using an approximation of n rectangles. Okay. The actual area then is the limit as n goes to infinity of this a squared over 2 n plus 1 over n, which is equal to just a squared over 2, because a squared is a constant. This thing goes to 1, right? And that's good because we wanted a squared over 2 to be our area, because that's what we know the area is by just regular geometry rather than calculus. How did 2 get under the a? I just used the commutative property here. This is a squared n plus 1 over n times 2, right? And so then I put these two guys together as the fraction and those two guys together as the fraction and multiplied it that way instead. Yeah. Okay, questions on this one? Yeah. Okay. So I've got everything labeled here. I've picked out the kth rectangle, right? And this time I decided to use the right-hand rule. So this is my x value on the right-hand side of the triangle, right? So I put this thing into the function. This goes into f of x. And so my output is this. That's my y value of this coordinate, this point. And so the height of this rectangle would be the y value of that point. And so that goes into my height bit, right, the tall bit. And the width, we decided earlier that every rectangle was a over n wide. And so there's the width. But you could also just take this guy minus this guy to get the width. Yeah, does that make sense? And so the area of the kth rectangle is this. It depends on k. I mean, a and n are fixed in this situation. So really all it depends on is the k value. Yeah. Do you need to do the width? So if they're all equal width, you can multiply by the width at the end. Sort of think of it as distributive property and take it out early. But if you have differing widths on your rectangles, you want to add them all up individually. Does that make sense? For our purposes, you could take it out at the end, but you need the width in there to find the area of the rectangle. Yeah. Even though that width is shrinking to 0, you still need to keep it in there so that in the limit, you see what happens, right? If I just didn't think of it, then I'd be adding up a bunch of 0 stuff. So there has to be something there. Otherwise, it kind of, the dimensions just don't work right if you do it the other way. Other questions? Today's Thursday, right? Okay. those all start at zeros, which is nice. The partition? Yeah, okay. So the norm of the partition is it's either the greatest width or the smallest width. Let me look here. Largest width. That makes more sense. It's the largest rectangle in that partition. So the partition is where you put the endpoints of your rectangle, where you put the verticals in. And so the widest rectangle of that partition is what the norm is. So let's do maybe an example. So you've got an x-axis and you've got this partition from A to B. And let's say that A is, we'll just do 41 here. We're going 0 to 3. This is 0. This is 3. And then I put in a 0 and I put in a 3 because the biggest point in the partition and the smallest point in the partition are going to be the endpoints of the entire interval that you're dealing with. And then we've got something at 1.2. We've got something at 1.5. We got it at 2.3. We've got at 2.6. So I've got rectangles, one rectangle there, one rectangle there, one rectangle there, one rectangle there, one rectangle there. 1, 2, 3, 4, 5 rectangles. The widest one we haven't figured out yet. This one is 1.2 wide, 0.3 wide, 0.8 wide, 0.3 wide, and 0.4 wide. So the widest one is this one. This is going to be the norm of the partition. Okay. But oh. There's a couple other nice ways that we can sum up things and make things easier. And let's just talk about one of those here. A summation is telescoping. If a part of one term cancels with a part of a later term. And I'll give you an example here. Let's say I want 1 over if I want to sum this up, right now I would have to add up 1 over 30 plus 1 over 42 plus blah, 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 whole bunch of stuff together, right? Okay. So what I'm going to do instead is I'm going to recognize that this thing in here, I could also write this as the sum from n equals 5 to 30 of, this is positive, so I want 1 over n minus 1 over n plus 1. And you guys might not have recognized that right away, but this is a common enough thing that if you have 1 over 2 numbers next to each other multiplied, then you've got a fractional, the difference of the fractions with the denominator. If I find a common denominator here, right? The denominator is going to be n times n plus 1. I'm going to have n plus 1 of them here. So this is going to look like n plus 1 over n times n plus 1 minus n of them over here, n times n plus 1. The n's cancel. I'm just left with 1 over that, right? Which is this. So I can split this up into these two things. And the book already does that type of stuff for you when it's dealing with these telescoping things. But now watch what happens when I write down this sum. I've got 1 over 5 minus 1 over 6 plus 1 over 6 minus 1 over 7 plus 1 over 7 minus 1 over 8 plus dot, 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 plus 1 over 30 minus 1 over 31, right? Let me go one shorter so we see what happens at the tail of it too. So 29, 30 plus 1 over 30 minus 1 over 31. Okay, minus 6, 1 plus 6. Minus the 6th plus the 6th. Minus the 7th plus the 7th. This minus an 8th is going to cancel with the next guy, which is a plus a 1/8. And then the 9th is going to cancel with the 9th. And the 10th is going to cancel with the 10th, right? And the 29th here is going to cancel with the 29th there. And the 30th is going to cancel with the 30th. And so what this does, like those old-timey telescopes where you can like slide them out and in, looking glasses or whatever you want to call them, right? This whole sequence just sort of collapses. All the middle stuff cancels each other. And I get 1 over 5 minus 1 over 31 as my entire summation. And so the telescoping, it just collapses. And this is going to be 31 minus 5 over 155, which is 26 over 155, which I don't think 13 goes into 155. No, it wouldn't. So we'll get that. So that's a telescoping sequence. Like the book has one here. Sum 7 to 27, square root of k minus 4 minus the square root of k minus 3. So this is going to be telescoping because this is k minus 4 and this is k minus 3, right? They're still under the square roots. They have an opposite sign, but subsequent terms are going to match these guys up, one of them with a plus sign, one of them with a minus sign. So I'm just going to write down the first few terms. I'm going to have the square root of 3 minus the square root of 4 plus the square root of 4 minus the square root of 5 plus the square root of 5 minus the square root of 6 plus dot, dot, dot. Plus, let's do the 26th term, put parentheses here. This is the k equals 7, k equals 8, k equals 9. Put in k equals 26, and then I get the square root of 22 minus the square root of 23. And then the k equals 27 guy, square root of 23 minus the square root of 24. Okay, those cancel, those cancel, those cancel, that cancels with this guy. That cancels there, this cancels there. I'm left with the square root of 3 minus the square root of 24. So the k equals 27. When I put it into the formula for the summands, I get 27 minus 4 is 23. Yeah. Questions on any of this stuff? Okay, you got questions on this? You can ask tomorrow and on Monday, because this stuff will be due Monday, right? Okay. The geometry can be a little tricky. Work on some of that. The algebra stuff, it's not so bad, but getting used to the notation can be kind of frustrating at times, because you got to really keep track of what the index variable is, and you have some other variables that are floating around in there maybe, but the only one that's changing in the summation is the index variable, right? We saw that we could pull out the n, we could pull out the a, that type of stuff. So keeping track and being organized is kind of tricky for some of this stuff, but it's not too bad. I will see you guys tomorrow.